Okay, so hi everyone, I am Santiago Jaraba Gomez, a PhD student at the Institute of Theoretical Physics in Madrid. And I'm going to present my work, Black Hole Induced Spins from Hyperbolic Encounters in Dense Clusters, which was done in collaboration with Professor Juan García Bellido. First of all, the aim of the work was to study the spin induction effect of initially non-spinning black holes, which are involved in close hyperbolic encounters. This is based on the work of Patrick Nelson, Zachary Attain, and other people who already studied this effect, but only for the case of equal masses. Now, our approach is different in the fact that we introduce different masses, we study the trends for different parameters with more detail, and we also draw some implications for real populations of black holes, in particular primordial black holes, which are formed without spin and in clusters. Now, in order to do this, what we do is perform a series of numerical simulations with the Einstein Toolkit. Here we show the initial conditions. Basically, we have a pair of black holes separated by a certain distance, which is fixed, each of them with their own masses and momenta, which are fixed to be symmetric. And we also fix the initial spins to be zero. Therefore, we just have three free parameters to play with, which are the initial momentum modulus, the incidence angle, and the mass ratio. Okay, so here I wrote some of the terms that were used within the Einstein Toolkit. And I also wanted to mention some of the technical issues that arise when simulating hyperbolic encounters, as opposed to simulating binary black holes, which basically arise from the fact that they require more space, which means that we need a larger grid, more refinement levels on the adaptive mesh refinement scheme. And all of this is basically translating into the need for more computational power and time. Also, if we introduce simulations with different masses, we are breaking the symmetry of the simulation. And this means basically that we need even more resources. In particular, this gives problems for a mass ratio which is very slow. And therefore, we just focus on this range of mass ratios here. In particular, our study will be centered on the dimensionless spin parameter. Here I show a typical output of a simulation. First of all, we show the strain amplitude of the emitted gravitational wave. We also show the spin evolution with time. First of all, we see that the black hole starts with a zero spin, then both of the black holes strongly interact, and then they end up with a constant non-zero spin, which is the value that we're going to be interested in. Okay, so if we do the same but varying the incidence angle, we end up with similar curves, but with less amplitude as we increase this parameter. This is more clearly seen in this graphic here, in which we plot the final spin with respect to the incidence angle for different values of the initial momenta. In particular, we can also see that all of the curves fit reasonably well to power laws, which are the curves that are superimposed. Now, if we move on to do the same study but varying the mass ratio, what we get are some curves like this, in which we can see that the spins induced for each mass participating on the same simulations are different. And in fact, the highest spin is induced on the most massive black hole, as can be seen in this figure here. Now, here I plot the final spins versus the mass, which in fact we can see that they fit reasonably well to straight lines, at least for locally for the region that we consider. And seeing these trends for these parameters, we try to come up with a weak field analytic approximation in order to see if we could predict them with simple approximations. Now the results are that we can predict some of the trends, such as the spin decrease with the incidence angle and the fact that the higher spin is induced on the most massive black hole. But this approximation obviously completely fails to predict the trends in quantitative terms, which was expected since we would need a post-Newtonian approximation of order 4 in order to correctly model the spins and give accurate predictions. Now, finally, we also simulated an encounter with mass ratio of 0.1 in order to see what were the main differences with respect to the other cases and if it was really that hard. First of all, we found that this simulation was much more time consuming than the other ones due to the extra refinement levels that are required. Here I included some of the typical times for the simulations to run on an HPC cluster. And in fact, we can see that the increase is very relevant. But this is not the only problem. For example, we also found that the center of mass gets displaced by a lot, which can impact some of the quantities that are derived from the Weyl scalar, such as the strain amplitude, because they are measured in spheres centered at the origin of coordinates, and therefore this makes it necessary to make some corrections. We also find that there is a drastic change of the limiting angle between hyperbolic and non-hyperbolic events. This was controlled before, and so we could very well control when we had a close hyperbolic encounter or a merger. But now that limit has completely changed, and therefore simulations that we expected to produce a close hyperbolic encounter can end up producing a merger. This is in fact what happened for this simulation. Here we show the strain amplitude after the corrections, which in fact perform very well. And here we show the spin evolution both before and after the merger. Now, even if these simulations ended up in a merger, we can draw some conclusions. For example, we can confirm the previous trend that the higher spin is induced on the most massive black hole, even for this low Q simulation. And we can also see that just because of their dynamics, some relevant spins can be induced before a merger. So finally, the main conclusions that should be drawn from this work are, first of all, that the spin induction effect that was previously reported is not lost for simulations of different masses, which could have been the case. In fact, for this type of simulations with different masses, the highest spin is induced on the most massive black hole. Also, we must conclude that the weak field approximations do reasonably well when predicted trends in qualitative terms, but they are clearly insufficient to give accurate predictions for such strong interactions. Now, the main conclusion that should be drawn from the previous simulation is the fact that two initially non-spinning black holes can acquire relevant spins before they merge just because of their dynamics, which should make us be careful with parameter estimations from the real gravitational wave events, because the estimated initial spin could have been lower originally. Now, finally, we conclude that this is a viable spin induction mechanism for primordial black holes, which are clustered and produce a lot of these kind of events, but a more detailed study of the spin distribution is left for future work. That is all. Thank you for your attention, and I am open for questions.